Hello, I'm Alessia Perilli, R&D scientist for FVMat, and today I present our recent work on AI-driven design, simulation, and optimization of novel metamaterials, focusing on both heat transfer and mechanical properties. FVMat is a deep tech startup developing metamaterial design tools that combine machine learning with multi-physics simulations. We are extending our AI solvers to lattice structures and broader computer-aided engineering applications. Our tools empower industries to simulate real-world conditions and optimize product performance. And we operate in aerospace, defense, and automotive sectors, generating revenue through software licensing and consulting. Let's start with the challenges in traditional heat transfer solutions. Modern systems face increasing thermal loads that exceed the limits of traditional cooling solutions. Conventional materials cannot provide tunable or anisotropic thermal responses. And what we need are compact and efficient thermal management solutions that can go beyond bulk material capabilities. Metamaterials can offer a solution to this problem in the sense that they offer unique properties which come from engineered microstructures and not necessarily composition. But our company developed a novel concept of metamaterials based on a structure which is a repetition of unit cells made of a solid matrix and a void inside of it, which can be filled with a substance, can be fluid, solid, particles, or a gas. And this kind of metamaterials have properties that vary spatially. They can be externally controlled, and they can adapt to environmental conditions. Let's start with an example of this kind of metamaterials. We design dynamic metamaterials by combining different phases, like solids and fluids, to achieve directional heat conduction, for instance. And an example is an orthorhombic unit cell, like in this figure, with a similarly shaped void inside, partially filled with a fluid. The thermal behavior of this unit cell is governed by void geometry and the interaction of the solid and fluid phases. The physical properties in terms of heat conduction can be reassumed in the thermal resistance of such a unit cell, and this property can be calculated semi-analytically based on a series and parallel of composite materials. And one can define a thermal anisotropy factor that quantifies the directional differences, defined basically as the ratio between the conductivity along two different axes. Now, simulating heat flow through such complex microstructure is critical to achieve controlled directional thermal properties. But simulating arrays of hundreds or thousands or millions of these unit cells is computationally expensive. We need to mesh and simulate every distinct zone, solid, the fluid, the air, which becomes resource intensive and time consuming. To tackle this, we generate a large data set using high-fidelity simulations by varying the geometry, the material, the temperature, and then we train machine learning models to predict thermal conductivities along the three axes. This machine learning model, which predicts the thermal behavior of a unit cell given their properties, can be embedded in finite element software for fast real-time predictions, enabling efficient simulation of large-scale, spatially varying metamaterials. Our machine learning model uses 4 physical unit cell features and temperature as inputs to predict as an output the anisotropic thermal conductivity in X, Y, and Z direction. All the training data are generated by finite element simulation, varying the geometry and the temperature. We validated this model on 10 by 10 by 10 array of unit cells. And the full finite element simulation for this structure took around 21 minutes to run, while using our machine learning-based tool, it just took 23 seconds, showing comparable accuracy. This shows the power of combining the machine learning tools with traditional finite element simulations, which is a huge gain in computational times. Here is a movie that shows the comparison between the full finite element simulation and the AI-based software that we developed. Here, I show how to construct the 10 by 10 by 10 array of unit cells with a full mesh of the solid part, the fluid, and the air. I show a section just to make sure that the meshing was fine enough. And also here another section of this solid, of this body, composite body. The boundary conditions is the temperature imposed boundary condition at the bottom and convection, all the other phases. And now the simulation will start, and we skip 20 minutes of the solution being computed. There's also a warning that the time was too long. And in the end, we get a temperature profile of in this body with a high temperature on the bottom, where the temperature was high temperature was imposed as a boundary condition, and a temperature profile going from hotter to colder until the top, with a very specific profile. The total elapsed time was 20 minutes, 15 seconds. Here I show the same simulation with our AI-based tool, with the same geometry. So I have 10 by 10 by 10 unit cells, 10 by 10 by 10 unit cells. The simulation starts with the same boundary conditions, and it just takes 27 seconds to get the solution. We get the results, and the temperature profile after 27 seconds is very similar to what we've seen in the full detailed finite element simulation, with a much reduced computational time, which orders of magnitude. Let's move on. Beyond thermal applications, we've also developed metamaterials for mechanical performance, enabling shock absorption, stiffness tuning, and vibration damping. Let's look now at two validated concepts that demonstrate our capabilities. The first concept is a unit cell that features a void with a lump mass connected by springs. And under impact, the internal mass moves due to inertia, delaying force transfer and reducing peak acceleration. We can tune the mechanical response by adjusting the internal mass, the spring stiffness, and the structural compliance. Simulation results show up to 30% reduction in peak acceleration and 70% impact energy absorption. Here we have also a movie that demonstrates a comparison between a bulk material and a unit cell, and how the bouncing of our unit cell is much delayed with less acceleration compared to the traditional empty box. An empty box on the left and our unit cell on the right. And we basically look at the velocity as a versus time, as a function of time, of the empty box versus the unit cell. And the red line is the empty box, and the purple line is the velocity of our unit cell. And we can see that the acceleration is much less, and also the bouncing of the unit cell is much delayed with respect to the empty box. The second concept is a unit cell with a void filled by viscous fluid, which enables energy dissipation through fluid motion under impact. Indeed, the internal fluid flow absorbs most of the kinetic energy, and the slope, if you look at the velocity as a function of time on this graph, again, the red would be an empty unit cell, and the purple is our unit cell filled with fluid. The acceleration, which is the slope of the curve, is incomparably less abrupt. And tuning the matrix stiffness, the void shape, and the fluid properties, again, we can optimize the impact performance. In this movie, We see a simulation of this unit cell under impact. And on the left, on the top left, we see the graph of the velocities, remembering that the slope of this curve, which is velocity versus time, is the acceleration. So the acceleration and then the force of the unit cell is much reduced, and a rough estimate would give at least 90% impact energy absorption. And this, it's a promising direction for designing protective materials with embedded damping properties. Here we see a typical viscoelastic modeling of fluid field unit cells using a classical linear model to describe viscoelastic behavior. We can write the Maxwell constitutive relation defining the instantaneous elastic moduli related to the long term and the initial elastic moduli, and linking also the elasticity tensor, the viscosity, and the strain rates. And all these parameters can be effectively derived from high-fidelity simulations to be used then in our machine learning models. And we used machine learning models which are trained on high-fidelity simulation data to predict such effective properties of fluid-filled unit cells. The model delivers near-instant results, making it ideal for rapid optimization and design exploration. In summary, we have demonstrated that machine learning-enabled metamaterial models significantly accelerate simulation and optimization. Our next steps include exploring more real-world applications, combining unit cell types for multifunctional materials, and expanding AI solvers to lattice structures and general purpose computer-aided engineering. Thank you for listening. Feel free to contact us at our email, and please follow us on LinkedIn. Bye.